Hello there, welcome to another lecture. So now that we've discovered the process of modeling and we've learned about a few basic and some a little advanced models. So basic models were just like 1R, naive Bayes, and then we've learned the more advanced classification models like decision trees. Now before we move to more advanced models like deep learning or support vector machines, I would like to stop here and talk about a very crucial and important step in the data mining process, which is the evaluation process. Okay, how do I judge the quality of the model that I've just built? Okay, how do I evaluate its performance? So this is what this module is about. So how predictive the model that we've just learned is. Okay, we want to know the predictive power of this model that we've just built. Now, what we've been doing so far is testing the training error, right? Remember, whenever I was assigning a WCAG homework, I was just asking you to use the default option of testing on the training data. So this is a very basic evaluation method where you are just assessing how the model is currently doing at learning and fitting the training data itself, which is a good indicator. Yes, it's giving us an idea about how well the model is doing throughout the learning process, but it is not enough, right? Evaluating the performance of the model on simply the training data is not enough, because this training data has been seen before. Okay, the model has already learned all the interesting patterns in this data. It already fitted this data. Sometimes some models can go up to 100% accuracy on the training data. Of course, we do not want that. Why? I hope you remember, because this is called overfitting, and it will prevent you from having a good generalizable model when testing it on unseen data. So you always want to have a not super complex model that reaches 100% on the training, but we want to be near 90%, maybe 85% and above on the training data. So this will give you an indicator that the model has been learning some interesting patterns in your training data, and now it's a good time to test this the quality of your model on unseen data, which is the we call the test data. Okay, so now to evaluate the model, I just mentioned training data and testing data. Okay, so this option is really, yes, it's simple, right? You only have two sets, one for training and one for testing. However, it is really a luxury. In fact, you can only do that if you have access to large amounts of data. So this will give you the luxury to split your data into training and testing splits. But sometimes you do not have this luxury of having large amounts of data. Then in that case, you need some alternatives to evaluate your model. So there are multiple considerations to think of when we are doing the model evaluation. For instance, as we just saw, there are multiple options when it comes to choosing the model, right? So we've learned some of the good models. So which one to choose for my data set, right? As we said, remember the no free lunch theorem? right? There is no one model that would solve all the problems and work for all the data sets. Therefore, how do I do that? The answer is experimentation. Okay, so you experiment with the data, you try multiple different models, and also read the literature, right? Go ahead and do a quick search about what is the state of the art for that particular problem. What did others try already, and what worked and what didn't work for them, so you can build on that and improve. Okay, so now that there are multiple models, let's say I do have three options. Okay, maybe I have decision trees, I have naive Bayes, and I have let's say a convolutional neural network. How do I choose? So I've tested three of them. How do I compare them? So there are multiple ways to do the model comparison in between. There's one way to do that is called the paired t-test. So it's a statistical based test that will tell us if one model is statistically significantly performing better than the others. So I hope we're going to have time to talk about this test and see it in practice, maybe through WECA homework or assignment, but I'm not going to start with this one. So another discussion that we have to think about, what is the metric that, or the measure that I'm going to use to assess the quality of my model? So far we have been using accuracy, right? So I asked you in some WECA assignments to report the accuracy, which is basically the number of correctly classified examples over the total of instances. Sometimes my model is not a classifier, which means it doesn't actually just give me the count of correct versus incorrect classified examples. Sometimes the output is a probability. So what do I do with that? How do I measure the performance of my model? Sometimes the output is a numeric prediction, right? Remember in the case of regression problems, how do I measure and evaluate my model then, right? So this is what this module is about. So we're going to learn in each one of these three cases what are the metrics and measures to evaluate the performance. Also, one important topic that we'll discuss is cost. Sometimes decisions and outcomes have costs. For instance, when a patient go to a doctor that uses an AI-based model that predicted that that patient is positive for cancer or any other disease or COVID-19, but that patient was in fact normal. He didn't have really COVID or cancer. So if you imagine the other opposite, where the patient was actually positive, but the AI model erroneously or incorrectly predicted that it was negative. So this second case is actually more costly than the first mistake, right? Because with the second case, the patient has actually the disease and it has to be treated immediately. However, we failed to do that because the model predicted his infection or his case as negative. So sometimes we do have costs per outcome, and we're going to talk about it a little bit in this chapter. So we said that the simplest approach is to have a train test split, where you train your model on the training data set. This is where the learning process happens, or the training, and then once you're ready, you go ahead and test the performance and evaluate the performance of your model on a separate testing data. Remember, we said that training error is optimistic. Why? Because the model have seen that data before. It knows it very well. It knows every aspect and pattern in that data set. So this is considered optimistic. in order to report and assess the quality of that model, you always have to test it on data that has never seen before. So one measure for the classification problem we said is the accuracy. On the other hand, you can use the error rate, which is basically, in the case of accuracy, an error means that one instance was not correctly classified. And then therefore to represent an error rate is basically the number of incorrectly classified instances over the total of instances that you have. And so remember, the testing data should take no part at all in the training stage. Okay, so these stages are two different ones. When you are training and creating your model, this testing data should not be involved at all. It is only at the end, when your classifier or model is ready, then you test on the unseen data. Now the training and testing data, remember, this still should have the same basis, which means that these two sets, these should be representing the same underlying problem. For instance, if you trained your model to predict cancer or non-cancer, then you shouldn't test your model on predicting some other disease like COVID, because these are two different diseases and they should have different features and considerations and patterns. Okay, so you should represent the same underlying problem, so stick with the same cancer or non-cancer topic. But then, for instance, during training, you are using data from a hospital in Tampa versus in testing, you are using data of patients from a hospital in Miami, right? So, but the data is the same. For instance, it's the MRI scans of those patients, except that the model has been trained on patients in Tampa and it has been tested in Miami. So the same underlying problem, however, the data is different in a sense that the model has not seen exactly the same patients before. So we are trying to predict the outcome on completely new patients. Now, a very important note here about the parameter tuning. So what do we mean by that? So each model will have a set of parameters that can change and vary. And I don't know which one is the best for my data set. So I do need a chance to experiment and fine-tune those parameters to my data set. Okay, so that's what we mean by parameter fine-tuning. For instance, for decision trees, we may want to choose the correct depth of the tree. We may want to change the metric that we're using. So instead of information, to choose the attributes, instead of information gain, I want to use something else like Gini index or gain ratios. There's multiple parameters that we have to experiment with and fine-tune depending on our problem and our data set. Now, we said that the training data is what we train the model on, and the testing data is what we evaluate and test our model on, and this should be really the final stage before deployment of the model. Now, in between, I want to be able to have some sort of a separate data set where I experiment and evaluate my model with some separate data while I do hyperparameter fine-tuning. So the idea is, sometimes if you have a luxury of having lots of data, then you can split your data into 3 sets. So the first is the training data. So you build one model here. You build a decision tree that has a depth of 10 levels. And then you have a separate set called a validation set, where you test the performance of your model. Let's say the model here reached a accuracy of 99%. Then once you test it on the validation set, then the model will, for instance, score let's see, we'll score just 80% accuracy. Remember, we said that once we test our built model on data that has never been seen before, it is very perfectly normal that the accuracy will drop because the model, it's a challenge for the model. It has never seen that data before. But we don't want the gap to be super aggressive, okay? We don't want something beyond let's say 20% drop, okay? That's bad. So it's anything like 15%, 10%, and so on, it's still acceptable, okay? Let's see. So let's say that the accuracy was 80%. Then I can go back to my training stage and modify the depth to, for example, let's see, to 6 levels. Then the training accuracy now will be maybe just 95%, and then the validation accuracy will now be 90%. So I just modified I just fine-tuned the parameter of my model to achieve better performance on the validation set. And then I can go back and forth doing these modifications to my parameters until I achieve an acceptable accuracy on the validation set. Only when I have one final product, one final model that is ready, then I can go back to the final stage, which is the testing stage. Then I can test my model, okay? So again, this is when you have the luxury of having big and lots of data. Now, once the validation stage is done, and you are satisfied with the results that you have achieved, and you finish the parameter fine-tuning stage, then you are allowed to put the validation data back in and join it with the training data to create a larger set, and then you retrain your model again, and then go ahead and test, okay? So again, remember, step number 1, train. Step number 2, validate and parameter fine-tune, and you can go back and forth as much as you want. Once you're done this part, then I said you can take this validation data back to the training set and retrain again before you move on and test. Why would I want to do that? Because a model trains better and achieves better performance with larger training sets, okay? The more data you have, the more interesting patterns you're gonna extract, the more your model is going to perform, okay? Now there's a dilemma here. So when I'm doing the split, there's two things here. Ideally, I want the training set to be as big as possible, okay? Because this will give me better performance. However, I do want the test set to be as big as possible too, because larger test data will give me more accurate error estimates, okay? I'm going to have a better idea on the error and a better estimation of the performance of the model when I have large test data. Because if I test my model on just 2 instances and I say, yay, my model got 100% accuracy on the test data, nope, you're wrong. There was just a 2 instance test. This is not representative of the real world, okay? So you should have a large test data in order to have an accurate estimation of how your model will perform in the real world, okay? Now this is a dilemma. So how can I split this? I want large training set, but I want large testing set. Well, yeah, it's a dilemma. I'm not sure how to solve it, but usually what we do is 80% for training and 20% for testing, okay? And this 20% can actually be split further into 10% for validation and 10% for testing. Okay, so now these ratios are subject to change, but the important thing is the majority of the data will go to the training stage because it's the most important. Okay, and then the rest will be then split into train and test, into validate and test. Okay, so now what if you have limited data, okay? So your company, for instance, did not provide you with separate sets. It didn't give you train, validate, and test sets separately. It just give you one single set and said, there you go ahead and build a data mining project. So there's other alternatives. Okay, so in this case you are limited with the data, but you can still split it. Okay, so usually we would keep 1/3 for testing and the rest is for training. Okay, and of course this split has to be random. Okay, so make sure you shuffle your data before drawing and creating a random split, 1/3 for testing and the remaining is for training. All right, now what if once I did the split, the samples or the instances in the test data, in each one of the mainly in the test data because it's the smallest one, may not be representative of the problem. Maybe once I did a random split, then I ended up with just one class in the test data. So this is a problem. So this set is not representative. So if I train on 3 classes and then I did a random split and suddenly all the instances in the test data only belong to one class, then that's not really an ideal scenario. One solution is to do stratification, so sampling with stratification. So we talked about this briefly in the beginning of the course. So stratification means we take our entire population. Let's say I have this data, okay, I have 3 different classes. So what I do is I create these groups of my data, and then when I want to do a random sampling, I want to do it by strata. So I will draw some instances from the first class, and then some instances from the other class, and then some instances from the third class, again randomly. Okay, so it's a random sampling, random split, but with stratification in order for us to keep the same representation as the original population. So one way to have more reliable evaluation or estimation, instead of doing the holdout method once, we can actually do something called the repeated holdout method. So instead of drawing one random split and then evaluating the performance on the test data, then instead of doing that, we can do multiple subsamples. So you did that once, you put that data back again into one population, and then you draw another second random sample and you test your performance on this one. Then you put it back, you draw another third sample, you test it again, and now you ended up with the 3 estimations. Then you use the average of all of the 3 of them. Okay, so now you have the estimation of how your model would perform on average. Okay, and we call this repeated holdout method. So this leads us to another evaluation method that is called cross-validation. So I'm sure you've seen this before as one of the options in Wake Up for testing. So cross-validation is another type of repeated holdout method, but it actually prevents or avoids the overlapping problem, because with repeated holdout we said that once you make a random sample, then in the next fold you put that sample back again and you draw another sample. So this will create some overlapping. Okay, now to avoid this we can use something called cross-validation. So the idea is you start by shuffling your data in the beginning, and then you split the data into k subsets of equal size. And then the second step is you use each subset in turn for testing, and then the remainder of the data you use it for training. So this means that the learning algorithm is applied to k different training sets in k different folds. And then at the end, you average the k accuracies. Okay. In this example here in the picture, you shuffle your data, right? And then the blue represents testing and red represents training. So here we have k folds. You can actually have any number of k. So you shuffle your data, and then in the first fold we're gonna use just these instances for testing and the rest for training. Okay, and then you're gonna get the first accuracy. In the second fold we're gonna use just this for testing, and then this and this for training. Okay, then you're gonna get the second accuracy. On the third fold we're gonna use these instances for testing and the rest for training. Okay, and this will give you a third accuracy estimate, and then you will average that out. So this is what cross-validation is. So it's like you built 3 models on 3 different training sets. Okay, so we use cross-validation again when you have limited data. Okay, it's just one set, but you are kind of trying to make your model more reliable and have more accurate estimates of the error. So you can use cross-validation. So we have k different subsets. In each fold you alternate. You use one subset for testing and the rest for training, and you do that k times. So this is another good visual. So for the k-fold cross-validation, so you can call it fold or also iteration. So in this case, k is equal to 5 in this example, and then at each iteration or fold, you specify one subset that will be used for testing. Here they call it validation because usually cross-validation is part of the validation stage. Remember we said train, validate, and test, right? So usually we use cross-validation in this stage. Okay, so one subset to validate your model and the remaining data for training. So you will get one performance outcome, and then in the second fold, this subset will be for testing, and the entire gray remaining instances will be used for training. This will give you a second outcome, and then you average all the 5 outcomes. Now there is one extreme case of cross-validation that is called leave one out cross-validation. So this is really, we use this when you really have very limited data. Okay, so let's say I only have 100 instances in total. So what do I do with that? Do I just give up and not build a data mining model? No, you do have this alternative of using leave one out cross-validation. So the idea is you are going to do 100 cross-validations. So you're going to do 100 folds or iterations. In each iteration, you're going to train your data on 99 instances and test on the remaining one. So you are leaving just one instance out for testing. That's where the name leave one out cross-validation came from. Okay, and then in the second fold, you're gonna leave another instance out, which supposed to be not this one. Okay, and then the other 99 use them for training. And you do that 100 times. Each time you are leaving one of the instances out for testing. So this is very computational expensive and very costly, because you're going to end up creating 100 models, okay? Again, you're going to end up with having 100 different accuracies that you will end up averaging at the end. So you will have to create as many models as much data you have, but again, it's only used in when you have very, very limited data set, just really very small amount of data. That's when you use leave one out cross validation. So now let me ask you this. So testing the model on training data is what? So if you use the training data to test and evaluate your model, what do you think? Is it pessimistic or optimistic or not useful? So you can pause the video a little bit to think about it. Now, we can't say not useful. It is very useful, because that's how you train and teach your model. It is actually optimistic. That's the correct answer. Why is it optimistic? Because, as we said, the model has already seen this data before and it knows all the hidden patterns. Okay, so if you just rely on the 99% on training data, this is really optimistic, and it doesn't give you a real estimation of how the model will perform in the real world. So testing data need to be what? Completely different from the training data, or independent from the training data, or representative of the same underlying problem, or small. So again, you can pause the video and think about it for a second. Okay, so do we want the testing data to be small? No, so we said we want as much data to test the model on, because this will give us a good estimation of how the model will perform in real life. Do we want it to be completely different from the training data? No. We said that we have to somehow keep the same statistical distribution for both the training and the testing data. It has to be independent, yes. We should never mix the training and testing data, as we said before, and it has to be, again, representative of the same problem. You cannot train a model to predict cancer, but you are testing it to predict a different disease, okay? Again, this is another quiz. You can pause the video to think about the answer. So the validation data does not have to be large. No, it can be any size really, but the important is that validation stage, or the validation data, serves as one way to fine-tune the parameters of the classifier. Okay, so we call this an under construction classifier, because it's not yet the final product. We're still fine-tuning it, and to do that we can use the validation data. It has to be a representative of the same underlying problem, and it shouldn't really be completely different from the training data, okay? It has to be independent, okay? Again, you can train on patients from Tampa, validate on patients from Miami, and test on patients from Gainesville, right? So you, again, still talking about the same underlying problem of cancer and non-cancer, but you are using independent sets to train, validate, and test.